Babies, how we doing today? Welcome to our next unit. We're going to focus here on what's called energy, work, and power. Today we're going to focus primarily on the ideas of energy and work and how they're related. So energy is something you might have learned about a long time ago in physical science. Energy is a substance-like quantity that gives us the ability to do work. Key thing here is that it is considered a substance-like quantity. That's kind of how I define it, because it is something that can be transferred. We might eat, for example, we might need food that give us energy. We might have an object be able to throw something, give it physical energy in terms of its motion or its height. But it is something that it has that can be passed along, whether it's transferred from one object to the next, or maybe whether it stays internal inside of an object and goes from one form to the next. But big idea here, where the connection is today, is that energy allows us to do work. So work, again, is going to be a process like a job. It's going to be a process of taking that energy and utilizing it in some form. Okay, when it comes to the different types of energy, there are two types. There's what's called potential energy and kinetic energy. Potential, think of that word potential, means that you have the ability to do something, not now, but in the future. But potential energy is energy that's going to be stored. It's going to be stored due to, could be position, could be other things, but it's stored due to something. So there's all these different types I have here, like gravitational potential energy. So that's going to be energy stored due to height, chemical, elastic, nuclear, electrical. We'll look at these different types in our next section. Then you have kinetic energy. Kinetic is a word to represent motion. So it could be electrical kinetic energy, where we're looking at the motion of charged particles. It could be kinetic energy due to light, looking at the movement of light particles. You obviously have physical things like wind. You could have sound, which is the movement of energy through, and then thermal energy, which is the movement of particles and how we get heat and all that. So kinetic energy has to deal primarily with motion versus potential with energy being stored. All right, now how we measure energy. It can be your favorite freaking unit of the year, not unit in terms of what we're studying, but unit as in terms of how we describe energy, okay? So we describe energy in terms of a unit called the joule. Now, this is not named after your fantastic, stupid little joule thing that all the teenagers like to do because they're so freaking hip and cool. But when we talk about the joule, that rhymes, it's actually named after a physicist, Robert Joule, who came up with a simple apparatus that gave us a way to measure the amount of energy associated with something. So he came up with this little apparatus here, which is just a little hand crank that when you turn it, it was attached to a rope. That rope was hung over a pulley with a mass attached to it. And then inside here, we have there's, say, a liquid like water, for example, and a little fan, a little turbine that as you crank this, it's going to turn that turbine and at the same time is going to lift this mass up. And what he recognized is that as this object was lifted up into the air, as it gained a vertical distance, that he saw that there was an increase in temperature of the water. So what he was able to do is make a connection between a unit that we probably are familiar with called a calorie, which is where we get that internal energy to do something, and he related that energy to a physical movement of an object. So what he said is that a joule of energy is the equivalent to applying 1 Newton of force over a distance of 1 meter. The key thing is that this gave us a physical way to measure energy as opposed to things that we might have learned about in chemistry or in terms of calories, which is like that food energy or the internal energy of things that we might have. Now, this kind of brings up the process of work. Okay, so energy, again, gives us that ability to do work. So in that simple apparatus of spinning that little hand crank and spinning the turbine and lifting the mass up, what we did is by doing that, we're essentially applying a force. That in order for that mass to move up, in order for that wheel to turn inside that liquid, that there needed to be a force to apply. And then also that force is going to act over a certain distance. So again, that 1 joule we talked about was equivalent to 1 Newton of force acting over a distance of 1 meter. So the two variables you have here is you have force and distance. So there must be a force, push or pull being applied over a certain distance. And what this does is this allows us to bring in the concept of work. So work is obviously a process of doing something. So the idea here is that work is a process of adding and removing energy from a system. So if I do, let's say, for example, positive work is going to represent me adding energy to the system versus me doing negative work Negative work is going to represent me taking energy away from the system. And I'm going to do this by applying a force through a certain distance. Okay, so in a simple context, if I were to just take, let's say, an object that was resting on a surface, and let's say I take that object and I now lift it up in the air. Well, in order to do this, I must apply a force upward, and that force must be acted over a certain distance. But what I've now done by just moving that object is I've now given it something that it didn't have before. In this case, I'm going to give it potential energy. I'm going to give it energy stored due to that height. Now, how do I know that that object has energy? Because what we've talked about is that if I were to drop this object from this height, then obviously that object is going to fall. Okay, so it now has the ability to do something because I did work on it. I gave it energy, I gave it height that it didn't have before. And that object doesn't want to be at that height, so it's naturally going to fall back down. So by me doing something against its own will, I suppose, that is me doing work on it to add energy. I could do the opposite by lowering that object back to the ground and taking that energy back away. So primarily work is going to be equal to whatever that force is acting over a distance. However, based on what I do, there is some trig that kind of gets brought up in here. So you'll see here I have at the end times the cosine of theta. So the cosine of theta, what that's going to do is it's going to look at the force acting in the direction of motion. So I kind of have this over here. So if I apply a force in the same direction as its movement, that's going to give me an angle. I know that looks a little silly, but that's going to give me an angle of 0 degrees. Now, why the cosine is important is because here I'm looking at the force in the movement acting in the same direction. And when I take the cosine of 0 degrees, I get a value of 1, okay, which means that 100% of my force is going towards the direction of motion, okay? The complete opposite to that is, let's say that I apply a force opposite the direction of motion. Now, what we hopefully will know between the difference between these two in terms of motion is that this would normally cause an object to speed up. And if it's speeding up, it's gaining energy, versus this one would cause an object to slow down. And by slowing down, it's losing energy. Okay, now in terms of the cosine, why it's important is because mathematically the cosine of 180 degrees is going to give me -1. So what that does is it doesn't add energy, but it's going to take energy away. And in this last one, this is kind of confusing, but this is where the cosine comes into play, is that let's say that I apply a force upward and that object moves to the right. So what's happening here is that my force has nothing to do with the direction of motion. I'm applying a force upward and it's moving in a completely different direction than I'm applying a force. So here, if we think about the cosine of 90 degrees, the angle between those two things, what I'm going to get is 0. Okay. Now, what does this mean? This means that in terms of the very first case, this would be where positive work is being done. The next case, that would be where negative work is being done, taking away energy. And in this case, there'd be 0 work, which means even though I'm applying a force, that force is not adding or removing energy away from that object. All right, now the key thing here is that work must be done by what's called an external force. So an external force is going to be a force applied outside of the system, and that is going to be the thing that's going to cause the object to gain or lose energy. So for example, if I look at the energy of this crate, and it's obviously having a force applied by this person, that it is this person that serves as the external force, because if we're looking at the energy associated with that crate, that person is obviously not a part of the crate. Same thing here, if I go back to the whole apparatus that Robert Joule set up, is that the external force was whatever force was applied on the crank. That external force, obviously with the rope, is what caused the mast to raise up and what caused the turbine to spin. Without that external force, there would be no work being done. So work is always going to be caused by something outside of the system. First example is going to be simple here. We're going to look at just whether work is done. So when work is done, again, it is a force acting over a certain distance. And then we're also going to consider the angle in between them, okay? Key thing here is that we need to apply a force, push or pull. We need to see some distance, and then we also have to consider the angle between them. So first example, a teacher applies a force to a wall and becomes exhausted. So in this case, when you apply a force to the wall, yeah, it's going to be exhausting because you're applying a force. But in this case, since there is no distance, that means in this case there would be no work being done, okay? It says a book falls off a table and falls free to the ground. So as a book falls, let's think about this. Is there a force acting on it? Well, it falls because we have the force of gravity. And as it falls, it's going to fall a distance downward. So in this case, there is going to be work done. And we can consider here that work is going to be done by gravity. And since they're acting in the same direction, think of that as positive work being done by gravity. Okay, so here it says a waiter carries a tray full of meals above his head by holding one arm straight across the room at a constant speed. So imagine a tray of meals. So here's a tray, here's some meals on it. When he's holding that thing, he's applying a force upward. Now this is a sassy one, but it says he walks straight across the room. So as he's applying a force upward, he is moving forward. So in this case, if we think about what's important here is the angle between them. The angle between these two things is 90 degrees. And then when I do the cosine of 90 degrees, that's going to give me 0, which in this case means that there is no work being done. So as exhausting as it is, because the force and direction of motion are at a 90-degree angle to each other, technically that waiter does no work. This is very similar to example 1 where the teacher pushed on the wall didn't move. The only difference here is that because of direction, the force he's applying has nothing to do with the direction of the motion. Okay, your force is just simply to hold that tray in place, kind of like you pushing on a wall and it not moving. Lastly, it says a rocket accelerates through space. So a rocket, this one's tough to draw, so I'll just draw as a box. But how does a rocket accelerate through space? It needs a force to be applied, and that force would act in the direction of its motion. So again, this would be a case in which positive work is being done. There needs to be a force acting over a certain distance. So is it work? We're looking for a force being applied. Is there a distance? And then we also got to consider the angle between those two things. Our next one, just calculating work. So again, we're going to use that same relationship that work is going to equal force times the distance times the cosine of that angle. And again, the sassy part here is that cosine portion, but that cosine is just, again, kind of like projectile motion is going to look at what percentage of that force is actually giving energy or taking energy away. So in the first one, I have 100 Newton force applied to a 15 kilogram object to move a horizontal distance of 5 meters. So in this case, if you're given the force, you're given the mass, you are told it's going to move horizontally a distance of 5 meters. So if I were to use this equation again, it's going to be the force of 100 times the distance of 5, and then it's going to be times the cosine of the angle between them. Now, since my arrow is pointing to the right for the force and my direction is right, the angle between those two things would be 0 degrees. So if I were to calculate that amount of work, what I would get is a positive 500 joules. And again, joules, capital J, is going to be our unit of energy. That is how much oomph we give to the object. Now notice here in the second example, I have the same force, same object, still going to move the same horizontal distance, but now that force is acting at an angle. So again, when we think about forces acting at an angle, we know that this force has components. There's a part of that force that's pushing it forward, but there's also a part of that force that's pushing it upward. In terms of work, it is this one that is going to cause the object to move that 5 meters horizontally. So we need to find that. So just kind of putting it all together, we're still going to take our force of 100. We're still going to multiply it by 5, but now what we're going to do is we're going to use the cosine of that given angle, which is 30 degrees. Cosine of 30 degrees is going to give you a decimal like a percent. So now what we're going to do is take away from that 500 joules, and it's going to give us a percent of that 500. And what you would get here is about 433 joules. So give or take, rounding about 70 joules or so less than what we did before, and that is because it's not acting in the same direction. Last one says an upward force is applied to lift an object at a constant speed, now 5 meters. So again, we're going to lift this object. So now if it's being lifted, the distance it's going to move straight upward. Again, that's going to be 5 meters. We need to know the force. Okay, now this one just in a little extra sass here. If this object is 15 kilograms, what force would be needed to lift it at a constant speed? Hopefully you remember the relationship between the force of gravity and mass. That if I want to lift something, I need to overcome its mass. So it'd be 15 kilograms times gravity, which is 10. So that'll give us 150 newtons, which means that the force that I need to apply in order to lift this thing is 150 newtons. So kind of going back to find the work done, it's now 150 newtons times that distance of 5 meters. And again, the angle between this one, if it's being pushed or pulled upward and it moves upward, then the angle between them again is going to be 0 degrees, just like our first example. So that's going to give me a total amount of work, positive work here, of 750 joules. Okay? All right, so again, this is just being able to calculate work using that relationship. Depends on the force, distance, and then as well as the angle. All right, now it's just kind of relating back to things that we've done with forces. Again, the idea of balanced versus unbalanced forces. Back when we talked about Newton's laws, we said that when things are balanced, that all the forces are going to essentially cancel each other out, creating a net force of 0, and that object should move at a constant speed. Versus if things are unbalanced, we're going to see the object speed up or slow down or possibly change direction. So let's say in this case that we have a 10 Newton force being applied to this block on a frictionless surface. You'll see here there's no friction being applied. What is the amount of work done? So again, work is going to be equal to, just like we've been doing, force times your distance times the cosine of the angle between those two. So in this case, looking at these collection of forces, obviously the 10 Newton force, that's going to be the net force here. That's the thing that's going to be left over. And it's going to cause this object to move 5 meters to the right. So I'll just draw it down here that the distance, again, is going to be 5 meters to the right. So if I want to use this, again, this relationship, I'm going to take that 10 newtons times that 5 meters, and then again, the angle between the motion and the force is going to be 0 degrees. So in this case, it's going to give you 50 joules of work. All right? Same idea here. Again, I have 10 newtons now, whoopsie daisies, but instead of being my applied force, now we stop pushing and let friction do the work. So in this case, let's say that it's still moving to the right 5 meters, but now it's friction that's acting on it. Okay, so again, when we do this, it's still going to be our 10 newtons of force times our 5 meters, but now when I look at the angle between them, it's going to be the cosine of 180 degrees. Because the angle between right and left, the angle between my motion and my force is a complete 180 degrees. So what I'm going to see is I'm going to get the same answer, 50 joules, but in this case, I'm going to get a negative 50 joules. So what's the difference here? Is in this case, positive work means that we are adding energy. And in this case, negative work means that we are removing energy from the object. And again, this would cause the object to speed up. This would cause the object to slow down. So now we can relate this idea of motion and things we talked about to the concept of work and energy. All right, C and D. In C, notice all the forces here are balanced. I have 10 newtons right, now 10 newtons left of friction. Gravity and normal force are balanced. So in this case, my, whoopsie daisies, I did it again, my net force in this case is going to equal 0. So that means if I use my relationship here, of work equals a force times the distance times your cosine, your angle. In this case, I have 0 newtons. Even though this thing is still moving 5 meters to the right, it's now 0 times 5 meters, and it's hard for me to even describe the angle because 0 times 5, if I'm multiplying by 0, I know that there's going to be 0 joules of work done. And that is why this thing is going to move at a constant speed, because if it's moving at a constant speed, it's not gaining or losing speed, so therefore it's not gaining or losing any energy. All right, last one, it says an approximately 2 kilogram object is sliding at a constant speed across a friction-free surface with a displacement to the 5 meters to the right. So again, in this case, very similar to the last one, moving 5 meters to the right, but I don't know why I just put dm, but slide into the dm's when I meant d equals 5 meters, okay? But in this case, again, the net force is going to equal 0 newtons, okay? And heck, even if you look at these two forces, 20 newtons up, 20 newtons down, they're not even acting in the same direction. But again, this is going to give you 0 joules of work because all the forces are balanced. So again, in terms of work, we're looking at the force, the distance, and that angle. And now I want to focus on the idea, the difference between adding energy and removing energy. Little typo here, folks, but just kind of putting it all together. Again, we're going to calculate work using those same ideas. But it says, been traveling, carries a 200 Newton box up a flight of stairs, which has a height of 10 meters, and then pushes it a horizontal force of 50 newtons across the floor. And then I want to know how much work does he do during the entire motion. So imagine here there's a box at the bottom of the stairs. He's going to climb up, boop, boop, whatever. The object's going to come up here. Okay, and then he's going to take that object and he's going to slide it to a new location. It says here he's going to slide a horizontal distance of 35 meters, and here he's going to lift it 10 meters into the air. Obviously, he's just going to use stairs to do it. Okay, so in this case, we have two parts of the motion, so I'll just label this part 1 and then part 2. So for part 1, again, we're going to need the force. To find the amount of work done, it's force times the distance times the cosine of the angle. Okay, now in order to lift this object, we know that it's a 200 Newton box. Just real quick, in terms of the forces, if we think of gravity that's acting on it, we know that gravity is going to be 200 newtons. That's how much it weighs. So in order to lift this box, we need to apply at least an equal force of 200 newtons to get it lifted up. Okay, so that means the force that I'm going to apply here is 200 newtons. The distance I'm going to push it. Now I know that I'm using a flight of stairs. However, the distance we're essentially getting it to from beginning to end is that 10 meters. So we're applying that force for a total of 10 meters of height. And then since that object is being moved upward and that force is upward, the angle between them is going to be 0 degrees. So that's going to give me a total amount of work of 2,000 joules, 200 times 10 essentially. That's the first part of motion. For the second part of motion, we're going to do the same thing here, but now we're using a horizontal force. So here it says the horizontal force to push it is 50 newtons, and that force can be applied over a distance of 35 meters. So just like we did before, it's going to be 50 newtons times 35 meters, and then again the angle between them is going to be 0 degrees because they're being acted in the same direction. So that'll give me a total work in that case of 1750 joules. And then for the total amount of work done for the entire trip, just simply add those two numbers together to give me 3,750 joules of total work in order to lift that object and to push it to the right to its new location. So again, we are exerting energy to make that object do something different. All right, last example here. I want you to try this one on your own. So the goal is to calculate the amount of work done by that 2 Newton force. Now notice the angle I'm giving you is a little bit different. It says here that the box is going to move a horizontal distance of 4 meters. So think about this case. It's going to move 4 meters to the right, okay? And I want to know how much work is done. So why don't you guys pause this, give this one a shot. All right, here's what you should get for your answer. I know there's a lot going on, so I showed it. Using the simple formula, it'll be force times distance times the angle. So the force is 2 newtons. The distance is 4 meters, but now the angle is where it gets a little sassy here. So the angle I used is 60 degrees, and the reason why I used that angle of 60 degrees is because that is the angle between the force and the horizontal direction of motion. Now notice that's different than the 30 degrees that I got, but knowing 30 and 60 have to add up to 90. If that's confusing, we can go back to finding components. That if I know that this force is going up and to the right, it's got a rightward component and an upward component. So I used sine or cosine. I just showed both of them here. The horizontal component would be 1 Newton or 1.73 for the vertical component. And since this goes to the right, I could just take 1 Newton times 4 meters and get 4 joules as well. But overall, I should get 4 joules of energy due to that force. Okay, so again, this is looking at the relationship between work and energy, again, applying that force over a distance, considering the angle between them to either add or remove energy from an object. If you guys have any questions, jot them down. We'll see you in class.